We've learned how to do simple antiderivatives, integrals, but now it's time to tackle some more challenging ones. If you're comfortable with what we've done previously, and I called guess and check for lack of a better term, you're probably going to have a much easier transition to working with these more challenging problems. So I want to start off encouraging you to think about guess and check, and then slowly migrating to what we'll learn today in the more general cases. So let's just get started. Suppose I ask you to evaluate this integral. The integrand is 8x times the quantity x squared plus 1 cubed. If you want to try this guess and check technique, here's what a person that is trying that might go through in their thought process. First of all, I would say, okay, I see an expression with a power of 3 in that integrand, and I know the antiderivative with powers takes it up by 1. So I'm going to guess that the integral will end up with that expression raised to the third power instead being raised to the fourth power. So that's my initial guess in the guess and check method. Well, now how about the check? Am I right? Now comes the check part. You check by taking the derivative of your guess and see if you got it. So I'll take the derivative of the quantity x squared plus 1 raised to the fourth power. The general power rule says I've got to bring the 4 down, write the base down, reduce the exponent from 4 to a 3, and then by the chain rule, general power rule, chain rule, however you want to think of it, you need to go in and take the derivative of the base, which would be the derivative of x squared plus 1, and of course the derivative of x squared plus 1 is just 2x. And 4 times 2x is 8x. I would write that as 8x times the quantity x squared plus 1 cubed. So, am I right? Was my guess right? Look back. Is your check giving you the same thing you had in the original integrand? The answer is yes. My intuition about that was exactly right. So the answer is just what I had guessed, plus that constant of integration. You always have to add that for an indefinite integral. Don't forget that. If you understand what we're getting at here, everything else you'll do later is going to be easier. So I encourage you to think about this. Go back and rewatch this part of the video if you need to. This is extremely important that you get the idea of what we're doing here. In any case, that would be the answer. It's also possible that guess and check can work even if the guess doesn't turn out to be exactly right. And I'll tell you what I mean by that in a moment. But let's change that example so that I change that 8 to a 4, but otherwise it's the same problem we solved a minute ago. Change the 8 to a 4. The process starts off the same, nothing different about it. You identify your guess as being that expression raised to the fourth power instead of the third power, so the guess stays the same. You still test it by taking the derivative. Again, this is an exact repeat of what we just did. There's nothing different. Take the derivative of the quantity x squared plus 1 raised to the fourth power. That'll be 4 times the quantity x squared plus 1 to the third times the derivative of the inside, which is 2x. 2x times 4 is 8, so you get 8x times the quantity x squared plus 1 cubed. That's exactly what we did before. But this time, when I'm looking back and checking, I'm not quite right. I wanted to get a 4x where I got an 8x. Everything else is fine. Whenever I'm off just by a constant value, in other words, I needed a 4, but I got an 8. I'm off by a constant factor, just a numerical factor. Guess and check will still work. You just have to make an adjustment. So I got an 8 and I only needed a 4, so I'm going to guess half as much. So my old guess was the quantity x squared plus 1 to the fourth. I'm going to adjust my guess to just be half as much. Half of x squared plus 1 raised to the fourth. Now I'll check that guess and see what happens by taking the derivative of 1/2 my original guess. So if I take the derivative of 1/2 times the quantity x squared plus 1 to the fourth power, I take the 4 by the general power rule, I take the 4 and multiply it by the 1/2. Of course, 4 times 1/2 is 2. The x squared plus 1 drops from an exponent of 4 to an exponent of 3, and then I go back and multiply by the derivative of the base, and the base is x squared plus 1, so its derivative is 2x. And finally, 2 times 2x is 4x, so I end up with 4x times the quantity x squared plus 1 cubed, and when I go back and look, that in fact is right now. I got exactly what I needed. So the answer, because I got it right this time, is just my adjusted guess. So the integral of 4x times the quantity x squared plus 1 cubed is my adjusted guess, 1/2 times the quantity x squared plus 1 to the 4th plus the constant of integration. This is not that difficult, but you have to practice and think your way through this. And if that means pausing the presentation, going back through it again, that's fine. That's what you need to do. In any case, that would be the answer. Now, for those that aren't very comfortable with guess and check, or as the problems get more difficult in reality, we're going to learn a more formal way of doing this. But if you do want to use this more formal method, or if you don't want to use it, either way, actually, it's only going to work if you can get your guess within a constant factor of what the real answer is. And I'll show you what I mean by another example. What if I give you the integral 3x times the quantity x plus 1 squared and ask you to find the answer to that? The process, at least for what I'm trying to illustrate, will start off just the same as before. I see an expression with a power of 2, so for my first guess is to bump the power up to a 3. So my guess will be x plus 1 quantity cubed. Am I right? Well, I'll check it by taking the derivative. So I take the derivative of my guess. General power rule says take the 3 down front, drop the power on x plus 1. That should be x plus 1. Drop the power on x plus 1 down to a 2, and then take the derivative of the inside, and the derivative of x plus 1 is just 1. Again, that 2 should not be there. So my check gives me 3 times the quantity x plus 1 squared. Well, the x plus 1 quantity squared is there, and the 3 is there, but the problem is, when I'm comparing those two things, there's an x in the integrand that did not show up in my check. So just like before, when it was off by a factor of 2, I wasn't exactly right. Here I'm also not exactly right, but the problem is more serious. I'm not off by just a numerical factor. Before I was just off by a factor of 2, so I just had things. You can't be off by a factor involving a variable. If you're off by a factor of x or anything involving x, then the technique simply fails. And if it fails, you have to either back up and try a totally different technique, or it's possible if you just make up a random integral problem, you simply can't solve it. But for our purposes, there will generally be a different way to do it if you can't do it by this technique. But the point here is, your guess and check, or actually what I'm going to show you in a bit, will not work if you can't get to within a constant factor. That's the point of this. Okay, let's get to the punchline. I still encourage guess and check as a general proposition when the problem is not too bad. But as we get more difficult problems, this new method, which we call substitution or integration by substitution, is something that you'll probably want to learn how to do, because it just standardizes the procedure. It gives you a rote process to go through. And I think for the more difficult problems at least, and even for the simpler ones for some of you, it's the way you're going to want to do these problems. So let's just jump into this. And let me say before we begin that if you want to call this a trick, the trick is to fit that integral into this formula. The integral that you're given has to be fitted into this formula that tells you how to get an answer. And the best way to illustrate that is through an example. Suppose I want to integrate the quantity 4x times the quantity x squared plus 1 cubed. I'm sort of going to list a series of steps that you would go through as you do this substitution process. The first thing you want to do is figure out what u is. And in this case, u is going to be the expression that's raised to the power. That's going to be the x squared plus 1. Right there. Then you've got to compute the derivative of u with respect to x. Du dx, and that's going to be 2x. And then you wanted to solve it for the differential u, so you're going to multiply both sides of that by dx, and you'll end up with du is equal to 2x dx. And in reality, you can skip this step if you like, because you can see where you're going. You can go ahead and say that du is 2x dx without having to write down that second step. So step 2 is skippable, easily skippable as you get more used to doing these. But I put it in the beginning just for emphasis. Step 4. If the integrand has a numeric that is a constant factor, move it outside the integral. And you see here that numeric factor is 4. So the best thing to do is just to get it out of the way by moving it outside of the integral. Next, and this is the important part, well, it's all important, but this is a crucial part. Reconstruct the integrand so that the u part is followed by the du part. In other words, you're going to make a substitution, hence the name, but you need to get the u stuff together and the du stuff together so you can do that. So you notice, I hope, that the du has an x and a dx. And the integrand has an x and a dx, but they're not together. So the idea is to put them together. So I'm going to rewrite that so that the x gets moved over next to the dx. And the reason I want that is I see that they're together in the differential. Okay, once I do that, I've got to remember that the first part of the integrand is going to be the u part, and that works perfectly. The u is the base of that exponent, so it's going to be u raised to the third power. But the du is not quite right. I'm missing a factor of 2. But remember, when I talked about guess and check, it's okay if I'm off by a factor that's numerical, just a constant. So I'm okay to be off by a factor of 2 because I can put a 2 on the inside as long as I compensate by multiplying by 1/2 on the outside. Whatever factor, numerical factor you add on the inside of the integrand has to be compensated by its reciprocal on the outside. That is so crucial, and if it takes you an hour of going back and forth, working this problem again and similar problems to make that click in your brain, it is well worth your time because this is a critical step. But once you do that, you can see that you've got a clear substitution. You can get rid of all your x's and just put in u's, because the first part of the integrand is the x squared plus 1 cubed. That just becomes u cubed. And the second part of the integrand, the 2x dx, just becomes du. So once you get it just right, you can see the u is the x squared plus 1 part, and the du is the 2x dx part. So you can just get rid of all your x's, and it turns the problem into the integral of u cubed times du with a 1/2 times 4, which is 2, out front. I cannot emphasize how important it is for you not to just cover up any misunderstanding about what's going on. If it takes you an hour, 2 hours to understand what's going on here, it is well worth your time to spend it, because if you get stuck here and you never quite understand what's happening, it's going to haunt you the rest of the semester. So please take me seriously here. But at this point, we've got 2 multiplied by a simple integral that fits the formula up above. The formula up above says if you've got a number multiplied by u to a power, you can get an answer. And the answer is, just write the number back down again. In our case, the number is 2. Just write the 2 back down again. And to get the answer for the integral, you increase the power of n by 1. It's like the guess and check. And then you compensate by 1 over n plus 1. So that 3 becomes a 4 exponent. The 2 just goes along for the ride. Using the formula, you raise the power by 1. It goes from a 3 to a 4. And then you multiply out front by 1/4. Whatever you raise the power to, you multiply out front by 1 over that power. And then never, ever forget you have to add that constant of integration on the end. And now it's just a matter of taking 1/2 times 4, of taking 2 times 1/4, and you get a half. 2/4 is a half. And you get 2/4, which is 1/2 u to the 4th plus a constant of integration. And the very last step is to get rid of the u's, because the u's were not in the original problem, so the u's cannot be the final answer. In the end, you have to go back and remember that u stands for a function of x. So in this case, u is x squared plus 1. So in the last step, you'll go back and put x squared plus 1 in place of u, and that will be your final answer. Spend as much time going back and forth over this problem as you need, because if you don't understand it completely, it's going to haunt you. You have to understand this. I will say that we worked this problem earlier by guess and check, and if you look, they're the same answers. We got this answer by guess and check, and we got this answer by the formula, and they're the same thing. So just quickly pointing out that they're the same. Keep in mind that you can't force the integral to fit the formula unless it actually fits. So in the cases where you can't get within a constant factor of what you need it to be, then the method just fails. So let's illustrate that by taking the problem that we did earlier that we got stuck on by guess and check. Let's just take it again and show that this formula still won't get you there. But let's just see that. Go back to that problem, same one we worked a minute ago, or we tried to work a minute ago. You set u equal to the expression raised to the power, so that'd be the x plus 1. Then you take the differential, so you take the derivative du dx, which is just 1. Solve for du, that's du would just be 1 dx or dx. And again, that's a skippable step. You can sort of see in your head what's happening. You really don't have to do step 2 on paper. Then you look to see if the integrand has a numeric, which is a constant factor, and if it is, move it outside. And I do see that there's a numeric factor of 3, so I'm going to move it out front. It just pushes it out of the way, and you don't have to worry about it, because the derivative of a constant times a function is the constant times the derivative of the function, and the integral of a constant times a function is the constant times the integral of the function. So it works nicely. You can take constant factors and sort of separate them from the other work you're doing. So start off the same. I want to reconstruct that integrand so that the u part is followed by the du part. So I'm looking, the u part is the thing that's got the x plus 1 in it, so the u part will be here. I want to put the du part, dx together, but here's the problem. dx is just equal to du. This takes care of the u part, but you're still sitting here with an x that doesn't appear anywhere up here. And it doesn't appear in any of your calculations when you're trying to figure out what u and du are. That's a problem. That means you're off by more than a constant factor. You're actually off by a factor of x. And that tells you that the method fails. If you were trying to substitute out and let du be dx, you'd get a du here, and you'd get a u squared there, but there's nothing to do to get rid of that x. Whenever that happens, if you're off just by a number, you can factor it out. But when you're off by more than a number, the method simply fails. If the method fails, you either have to find another way of doing it, another method that works, or just conclude that you just don't know how to do it, or maybe it can't be done. In this case, though, we can do it because we know, might not enjoy it, but we can square out that binomial and just do it term by term. So we do know another method of doing this one, so let's just do it. If you square out that x plus 1, that's x plus 1 times x plus 1, and do the FOIL method on it, you'll get x squared plus 2x plus 1. And then if you multiply all those terms by 3x, you'll end up with the integrand of 3x cubed plus 6x squared plus 3x. And you can integrate those term by term. So just take the integral of the antiderivative of each term and add a plus c. So you add one to the exponent and divide by it. If you have to do it more formally, you can think of that 3 as just sitting there, and you add 1 to the exponent and then divide by 1/4. But 3 is 3 over 1, and you end up with that 3/4 right there. And again, that 6 can just sit there. You write the exponent higher and then multiply by 1/3, and 6 times 1/3 is 6/3, which is here. We'll simplify that to 2 on the next step. And then the 3 can just sit there, and you raise the x to the second power, and you multiply by half, so you end up with 3 over 1 times 1 over 2, which is 3/2. And then you have the plus c. So as we get more and more into this, I'm going to encourage you to think more like this rather than having to think of this as a separate step. But do what you need to do to get the right answer. And then finally, I would take that 6/3 and make it a 2. And that would be your final answer. Again, take as much time as you need to do these problems, because if you don't, it's going to hurt you later. The time you spend now is well spent time. Now, if you understand and are pretty comfortable with everything that we presented so far in this lesson, then you're really ready to evaluate all the integrals in your next assignment, if that's all true. However, I've never seen a case where there's not a pretty steep in some case, learning curve. Now, if you've had it before, had it in high school, done it before, maybe you've already been through that learning curve. But for most people, there is going to be a significant learning curve, and you have to practice and practice and practice. And watching someone else work the problems is not equivalent to practice. It might help you get ready for the practice, but if you're not putting in the time yourself and practice, more practice, watching someone, me or anyone else, do this is never going to be enough. So please take the time. So I just work some more problems. You might want to have those steps in front of you as you do this, but I hope at some point, in fact, some point relatively soon, it just becomes second nature and you don't need to think about it as steps so much. But anyway, you start off with something raised to a power. So that thing raised to the power is probably going to be your u. So u would be x minus 6. Then you compute the derivative of u with respect to x. The derivative of x is 1, the derivative of 6 is 0, so you end up with du over dx is equal to 1, which means du is just 1 dx, or du is equal to dx. And now you look back and see if you can substitute. Well, yes, you can. You're not even off by any factors. The x minus 6 becomes u, the dx becomes du, and you've converted that whole integral into something that has just u's in it, which is your goal. You get u to the 3/2 du. Now you're ready to use your formula. Your formula tells you what to do. If there's a constant, you just write it down. In this case, there's not one. But basically what you do is raise the power of u by 1 and multiply by 1 over that power out front and add a plus c. So if you add 1 to 3 halves, you get 5 halves, because 1 is 2 halves, 3 halves plus 2 halves is 5 halves, and you divide by 5 halves. And again, I hope at some point that becomes a skippable step, because 1 over a fraction just turns it upside down. So that 1 over 5 halves becomes 2/5. So I would hope at some point you could consider this to be a skippable step. You can just remember that 1 over 5 halves is going to be 2/5. And then, of course, the last step is to get rid of the u's. You know that u is equal to x minus 6. Get rid of the u's and put in x minus 6. And bingo, you have the answer. Another one. It's very similar to that one we just did, except I added a factor of 2. Similar to what we've done with some of the others, just more practice. What do? Well, your steps say if you have a constant factor, a numerical factor, however you want to say it, it's better to bring it out front. So I brought the 2 out front, but other than that, the process is the same. U will still be x minus 6, du will still be dx, and if you substitute back in, you'll get the same thing we did before, except you've got that 2 out front. And when you integrate the u to the 3 halves, you get exactly the same thing you got over here, because it's the same problem. The only thing is it's multiplied by 2. And again, 1 over 5 halves is 2/5. And again, I hope at some point that will be a skippable step for you, that you won't feel the need to write that down. You can just write 1 over 5 halves as 2/5 without ever writing down that complex fraction. And then, of course, 2 is like 2 over 1. So if you multiply those together, you get 2 times 2, you get 4/5. And then you get rid of the u at the end. Practice makes perfect. Let's do another. It looks kind of monstrous, but the process is the same. I see something raised to a power, so that's going to be my choice for u. The x to the 4th plus 6x squared. Notice that the rest of the integrand has an highest exponent of 3. You start out with the highest exponent of 4, so it's a good idea that you've made a decent choice for u, because you know when you take du, the power is going to go down by 1, and you have a good chance of matching, or the only chance of matching, actually. But anyway, if you calculate the derivative and solve for du, you'll find out that du is 4x cubed plus 12x times dx. Well, that's exactly what you have up here. You have exactly what you need. So you're going to let that become u, the first part, raised to the 5th power, and the rest of it is going to be du, excuse me. So when you substitute, you get u to the 5th times du. Everything came out perfectly. Use your formula. The formula says you add 1 and then divide by that 1 over that number, and then get rid of your u. It's really not that bad, but if you practice, you're going to get better. If you don't practice, you probably won't. How about this one? Very similar. I made a couple of changes. Let's see what happens. Start off the same process. There's no reason why the x to the 4th plus 6x squared can't be the same value of u. I know when I take the derivative of x to the 4th, I'll get something with x to the 3rd, so that's promising. Take the derivative, I get 4x to the 3rd plus 12x. Now that's not exactly, when I get du, that's not exactly what I have. But think about it a minute. There's a 4 inside of both factors in that differential. If I factor a 4 out, I get 4 times the quantity x cubed plus 3x. And notice now that that x cubed plus 3x appears there, and I'm just missing a 4. Think back to what I've been saying. If you're only off by a constant factor, a numeric factor, you can still do this. All you have to do is put it in there. So what I'll take the time to do is put that 4 in there. If you put a factor of 4 inside the integrand, you have to compensate by putting the reciprocal 1 over that thing on the outside, because 4 times a 4th is just 1, and net you haven't changed the value of the integral at all. So you can compensate by a constant, but you have to adjust on the outside by its reciprocal. But now that you have done it, you can see that you have exactly du right there, and you have u right here. So your integral turns into that 1/4, which is out front, times the integral of u, just u to the first. There's no second power, third power, fourth power, it's just u, times du. Well, now you use the power rule. The power rule tells you what to do. You raise the power of u up by 1, so it's an understood 1, so if you raise it up by 1, it'll be a 2. And out front, you have to multiply by the reciprocal of 2, which is 1/2. Don't forget the 1/4 is still sitting out there, so you have to take a 4th times a half and get an 1/8. And then your last step, you have to get rid of the u and put in the x to the 4th plus 6x squared. Again, practice makes perfect. How about this? We've got a radical in there. Well, a cube root is a 1/3 power, so I know I have to do that with these integrals. So I changed the cube root to a 1/3 power, and now I'm back on my same routine. I know what I'm going to try for u. I'm going to let u be the base of the 1/3 power. So it's going to be 1 minus 4x squared. Then I compute the derivative as minus 8x, so du is minus 8x times dx. Well, that's exactly what I have over there. So I can do a match right now. The 1 minus 4x squared becomes the u, and the rest of it becomes du, so I only have to integrate u to the 1/3 du. Now I go back to the formula. What does the formula say to do? Raise the power by 1 and then divide by it, or say it differently. Raise the power by 1 and multiply outside by its reciprocal. 1 added to 1/3 is 4/3. You divide by 4/3. Again, I think that's a skippable step. You can just go ahead and say that 1 over 4/3 is going to be the reciprocal, which is 3/4. And then you get rid of the u. Put back in what u is equal to, which is 1 minus 4x squared, and you got it. It's not so bad. How about this one? Very similar to the last one. I just changed the constant from a -8 to a -2. So the process should be very similar. I'll choose the same u, calculate du. Of course, that cube root was a 1/3. But now it doesn't match exactly. I got a minus 8x dx, but I only need a minus 2 dx. So the trick is, and if you go through the steps, the trick is just go ahead and move the constant out front and get rid of it. It makes it easier. Just take the factor of 2 out front. And now you can see that you need to put a minus 8 in where the minus 2 was. But if you do that, you have to compensate by multiplying by the reciprocal on the outside. So what you end up doing is putting that minus 8. You see that you needed a minus 8, so you put it in there, but you have to compensate by multiplying on the outside by the reciprocal, which is negative 1/8. Well, now it matches. The minus 8x dx becomes the du. The 1 minus 4x squared is the u. And then out front, you've got minus 2 times minus 1/8. And again, minus 2 is like minus 2 over 1. You've got a negative times a negative, which would be positive, so you get 2/8, and 2/8 reduces to a 4th out front. And the integral just becomes u to the 1/3. Well, that's just like what we did over on the other side. That's the same integral we got before. The only difference is you've got to multiply it by 1/4. So you use the formula. It says to raise the power by 1 and then multiply up front by 1 over that power. Again, the 1/4 just sits there, but 1 over 4/3 is 3/4. 1/4 times 3/4 is 3/16. And then get rid of the u at the end and put back in 1 minus 4x squared. Practice, practice, practice. How about this one? It's got a fraction, but I'm going to guess that the x squared is going to be part of the differential. And the reason I'm guessing that is that I think I'm probably going to choose the thing raised to a power to be the u, and the derivative of a third is going to end up with be a second power. So I'm assuming that the x squared is going to be part of the differential. So it would probably be good just to go ahead and put it over there. So if you take the x squared, remember that's like times 1. If you take the x squared and put it with the differential, that leaves you a 1 up top. Again, pause, think about it. that's probably the easiest way to think about it. You know in advance, if you practice this over and over again, that the differential part has to be put together. So I'm sort of anticipating that. I haven't even chosen a u formula yet, but I can see ahead enough to know that my choice for u is going to be 8x cubed plus 7. And one of the things that leads me there is I know when I take the derivative of a third, I'm going to end up with something squared, and that means that that x squared is probably going to be part of the differential. So I'll move it over there. Having done that, I can calculate the derivative. That's 24x squared, so du is 24x squared dx. Well, look, I have the x squared dx, but I don't have the 24. So that means I can adjust as long as I'm off by a constant. So I put the 24 in as long as I multiply by 1/24 on the outside. Having done that, I can substitute. I get 1 over u squared, and then the rest of it becomes du. So that gives me an integral of 1 over u squared multiplied by 1/24. Well, 1 over u squared is u to the minus 2, and now I can use my formula. I add 1 to minus 2, which makes it minus 1, and then I divide by it out front, or multiply by its reciprocal, however you want to say it. 1 over minus 1 is just minus 1, so out front you end up with a negative 1/24. And you really don't have to simplify it any further in terms of positive and negative exponents, but you do have to get rid of your u and put an x's back in. And there you go.